How's it going, everyone? Welcome back. In this video, we're going to be going over the derivatives and integrals for the hyperbolic functions. Now, I want to begin this video by deriving the differentiation formula for the hyperbolic sine. Now, as you noticed in the previous video, there was a theme here that basically whenever we were working with hyperbolic functions, a lot of the times it was just easier to go to the definition in terms of exponential functions, and that's exactly what we're going to do here as well. So I'm going to go ahead and write down the hyperbolic sine in terms of the exponential functions. Okay, so we're going to have here y equals to sinh of x, which is equals to, now for simplicity here, guys, I'm going to go ahead and rewrite the sinh as 1/2 times e to the x minus e to the negative x. Okay, now if we want to find the derivative, let's see what we get. So the derivative here of sinh is equals to the derivative of 1/2 times e to the x minus e to the negative x, which, lucky for us, it is a nice simple derivative. Exponentials are nice like that. So we're going to have here 1/2 times the derivative of e to the x, which is simply e to the x, now minus the derivative of e to the negative x, which is giving us a negative e to the negative x, but a negative and a negative will give us here a positive, so plus e to the negative x. Oh, well, would you look at that? This is just the formula for the hyperbolic cosine. So it seems then that the derivative for the sinh is simply just the cosh, very similar to the derivative of sine, giving you the cosine. Now we could go ahead and obtain the derivative formulas for the remaining hyperbolic functions using a similar approach to the one that we just did, but there is no need for that right now. Instead, I'm just going to go ahead and give you the following derivatives for and integrals for the hyperbolic functions. Now I want you guys to note here that a lot of the derivatives and integrals are very similar to their trigonometric analogs. However, there are a few subtle differences here and there where we need to be careful here. Now notice that, as we just said, the derivative for the sine, or in this case the derivative for the sinh, was the cosh, just as the derivative of sine is the cosine. However, notice here that the derivative of the cosh is the sinh, which is not the same as our trigonometric counterpart, where the derivative of the cosine was a negative sign. In this case, there's no negative to consider. Another difference here is for the derivative of the sech, where we now have a negative sech times tang. Again, different than the derivative of the secant, which is a positive secant tangent. So careful there. Now, I will also like to mention that the formulas that I would expect you guys to memorize are these three: the derivative for the sinh, cosh, and tang, as well as their respective integrals. The rest of the formulas here, while we will be using them in class, I will not expect you guys to memorize them for an exam. And some of the homework problems, you will need to use them. However, you can freely refer to the notes here. Okay, so let's take a look at a couple of problems here. So we want to go ahead and find the derivative of h of x, which is x, times the hyperbolic sine of x squared. Now notice that this problem here will require us to use the product rule, since we are multiplying x times the hyperbolic sine. So put here product rule. So let's go ahead and figure out this derivative. So the derivative, h prime of x, is going to be equals to, now since we're using the product rule, it is the derivative of the first function that is multiplying here, so it's dx. The derivative of x is 1, times the second function, so sinh of x squared, plus, now it's x, times the derivative of the second function, which will also require us to use the chain rule. So we're going to have here the derivative of sinh is the cosh of x squared times the derivative of the inside, which is 2x. Simplifying things further, we obtain the sinh of x squared plus 2x squared times the cosh of x squared. And there we go. We obtain our derivative function. Now let's take a look at another example here. We're being asked to find the derivative of the ln of the cosh of x. Okay, so we go ahead and use the chain rule, where I'm going to go ahead and define the cosh as my u. So the derivative for the ln is going to give us here f prime of x is equals to 1 over my u, which is a cosh, times the derivative of u, so the derivative of cosh is sinh of x. Now we can leave our answer here as as sinh over cosh, but I'm just going to go ahead and rewrite this one here as the tanh of, and there we go. We obtain our derivative. Now, I would like to point out here that at this point, we're not learning any new derivative techniques or new integration techniques. We're just learning new formulas. So we'll just be using our derivative formulas in conjunction with the other differential techniques that we've seen, like the product rule, as we just saw in this example, the chain rule, as we saw in both examples, and the quotient rule. Now, with regards to the integrals, same idea. We're going to be using, for the most part, u substitution in tandem here with our new formulas. Now, I would say this, though, that we're going to be encountering later formulas in this section that we would be able to derive once we go over some of the new concepts and material from Chapter 8. But in the meantime, I'll just present the formulas as is. Now, speaking of integrals, let's go ahead and take a look at one problem involving an integral. Okay, so for this problem, we're asked to evaluate the integral cosh of 2x times sinh squared of 2x dx. Okay, so this one here, it seems like a typical problem where we will need to use a u substitution. So we need to see if we can go ahead and identify what would be a nice choice of u. So for this problem here, notice that we are taking the sinh and we're squaring it, so that's a good sign that, hey, probably our u should be the sinh of 2x. Now, if that's the case, what would be our du? Well, our du is going to be the cosh of 2x times 2 dx. Now, at this point here, guys, we could go ahead and substitute our u and a du, while noticing here that our du has a 2 dx, which we don't have a 2 dx. We could go ahead and multiply by a 1/2 to correct the issue, which is perfectly true. That is the correct way, but again, if you're a little bit rusty with the u substitution, the trick that I was showing in previous videos is simply solve for the dx. So if we solve for the dx, we will be obtaining here dx is equals to 1 over 2 times the cosh of 2x du. So we could go ahead and now substitute both our u and our dx into the integral to obtain the following. We will be obtaining now the integral of the cosh of 2x times our u squared times our dx, which we now know it's 1 over 2 times the cosh of 2x du. And we get to see here that yes, the cosh of 2x cancels out. There is here a factor of 1/2 that we can take outside the integral. And we have now 1/2 times the integral of u squared, I'm going ahead of myself, du. Which, evaluating the integral here, we're going to have 1/2 times u to the third all over 3 plus c. Now go ahead and back substituting back to our x's, we're going to have 1/2 times, well, now I'll simplify it here as 1/6 times the sinh cubed of 2x plus c. And there we go. We evaluated an integral here. Now, as mentioned before, we're not learning any new integration techniques. We're just using our new formulas with a u substitution in this case. Okay, so now let's go ahead and take a look at some applications for hyperbolic functions. So let's take a look here at the problem below. Okay, so for this problem, we're asked to evaluate the integral cosh of 2x times sinh squared of 2x dx. Okay, so this one here, it seems like a typical problem where we will need to use a u substitution. So we need to see if we can go ahead and identify what would be a nice choice of u. So for this problem here, notice that we are taking the sinh and we're squaring it, so that's a good sign that, hey, probably our u should be the sinh of 2x. Now, if that's the case, what would be our du? Well, our du is going to be the cosh of 2x times 2 dx. Now at this point here, guys, we could go ahead and substitute our u and a du, while noticing here that our du has a 2 dx, which we don't have a 2 dx. We could go ahead and multiply by a 1/2 to correct the issue, which is perfectly true. That is the correct way, but again, if you're a little bit rusty with the u substitution, the trick that I was showing in previous videos is simply solve for the dx. So if we solve for the dx, we will be obtaining here dx is equals to 1/2 times the cosh of 2x du. So we could go ahead and now substitute both our u and our dx into the integral to obtain the following. We will be obtaining now the integral of the cosh of 2x times our u squared times our dx, which we now know it's 1/2 times the cosh of 2x du. And we get to see here that yes, the cosh of 2x cancels out. There is here a factor of 1/2 that we can take outside the integral. And we have now 1/2 times the integral of u squared, I'm going ahead of myself, du. Which, evaluating the integral here, we're going to have 1/2 times u to the third all over 3 plus c. Now go ahead and back substituting back to our x's, we're going to have 1/2 times, well now I'll simplify it here as 1/6 times the sinh cubed of 2x plus c. And there we go. We evaluated an integral here. Now, as mentioned before, we're not learning any new integration techniques. We're just using our new formulas with a u substitution in this case. Okay, so now let's go ahead and take a look at some applications for hyperbolic functions. So let's take a look here at the problem below. Okay, so when a cable is suspended between two supports, the curved form is called a catenary. Now, the general equation for a catenary curve is the following. It's y equals to a times the cosh of x over a, where a is the height of the cable at its lowest point, located on the y-axis. Now, if a is less than 0, then it is an inverted catenary. Now, this might sound like a new concept, but I would argue that we've seen catenaries frequently in our lives. Now, we can see at one below here in this picture, where we have two chains here tied by some poles, and we get to see here this shape. This is a catenary. Now, you see them in your daily life, well, maybe. If you take a look here at some of the light poles, you'll notice that, well, they are bending due to gravity, so they are forming a catenary. Alright, so let's go back to this picture here. So for the catenary formed by the chain shown, where A is 12 inches, if the distance between the two posts is 4 feet, or 48 inches, let's see if we can go ahead and find the slope for the chain at the point where the chain meets the right-hand post. Okay, so I'm going to go ahead and make a graph here that models the situation that we're dealing with. Alright, so here's my xy plane. Now we're being told that the A, which is the lowest point here of the catenary in the y-axis, is 12. So here our A is 12. And we know here that the distance between the two poles is 48 inches. So all of this is 48 inches. So that means here that on the right hand side, this length is 24 inches. And this length here is also 24 inches. Now let's go ahead and form the catenary. So here is my pole. Here is the right pole. And here we have the catenary. It's an exaggeration here, but it serves a purpose. Alright. Okay, so what we're trying to do here is, what would be the slope of the chain at the point where it meets the right-hand post? So we're trying to find out the slope here. Okay, well, if we're trying to find the slope, then all that we need is the derivative, and lucky for us, well, we know that the equation for a catenary curve is y equals to a times the cosh of x over a. So putting things together here, we're going to have y equals to our a, which was 12, times the cosh of x over 12. So finding the slope here, we're going to have y prime is equals to 12 times that derivative of the cosh of x over 12 is going to be the sinh of x over 12 times that derivative of the inside, which is 1/12. So that's going to cancel the 12s. And we're just left with y prime is equals to the sinh of x over 12. Now, we want to go ahead and evaluate the derivative at a particular point, at the point where the chain is meeting the right-hand post, which, as we saw right now, it's at a distance of 24 inches. So let's see what would be the derivative at 24 inches. Well, plugging things in, we're going to have the sinh of 24 over 12, which is the same thing as the sinh of 2. Now, what is the sinh of 2 here? Because this is a word problem, and well, typically it's not good to give exact answers for word problems, as we do want to have some context behind the problem. So what is the sinh of 2? So for the sinh of 2, I'm going to go ahead and use a very similar approach as we did in the first video to evaluate the sinh of 2. So I'm just going to go ahead and rewrite it as an exponential. So we're going to have here the sinh of 2 is the same thing as e to the second power minus e to the negative 2 all over 2. Now plugging this one here into my calculator, I obtained a 3.63. And there we go. We obtained the slope of the chain when it's connected to the right pole. Alrighty, so now we're going to be switching gears a little bit, and we are going to be discussing the inverse hyperbolic functions. Now, I would like to point out that we will not be going into much detail on the derivation for the inverse hyperbolic functions like we did for the inverse trig functions. Instead, this one here is just going to be serving more as an introduction for you guys to see the formulas, so you're a little bit more familiar with them in the case where you may encounter them in another physics or an engineering course. Now, I would say that you don't need to worry about memorizing these formulas. If you were to need them for a quiz or, let's say, an exam, I will be providing them for you. So, here are the formulas for the inverse hyperbolic functions. Now, notice here, though, that just as we were restricting the domain in the case for the regular inverse of the trigonometric functions, we also need to be restricting the domain for the hyperbolic functions. Again, we will not be going into much detail, but I wanted you guys to have the formulas here. Now, for a little bit of practice, let's see if we can go ahead and evaluate the following inverse hyperbolic functions. Let's see if we can go ahead and evaluate the inverse of the hyperbolic sine at 0 and the inverse for the hyperbolic cosine at 1, and relate these values to the sinh and the cosh. Now this one here seems a little bit tricky, but at its core, ultimately what we're doing is we're taking a look at a function and its inverse. So let's see, what will be the sinh, or what will be the sinh inverse of 0? Alright, so according to the formula above, which you can see here, we're going to have the sinh inverse of 0 is equals to the ln of 0 plus the square root of 0 squared plus 1, which is just going to give us the ln of 0 plus 1, which is the ln of 1, which is 0. Now let's see what would we get for the cosh inverse. So the the inverse of the inverse of the hyperbolic cosine at 1 is going to be equals to, so taking a look at the formula, the ln of x plus the square root of x squared minus 1 is going to be equals to the ln of 1 plus the square root of 1 squared minus 1, which is going to give us here the ln of 1, which is also 0. Okay, so it seems like we're getting 0 for both of our evaluations. Now, how do these answers compare to the regular hyperbolic sine and the hyperbolic cosine? So let's see here. Now, remember that we're talking about a function and its inverse, so if we have a function and its inverse, the domain and the range switch. So in the case for the sinh inverse of 0, alright, so we inputted 0, so it means that we know that the output of the sinh is going to be 0. And I'll do this one here. So if we have y equals to the sinh inverse of x, and we just saw right now that a point on this function, on this curve, is going to be 0, 0, then a point on its inverse function, the hyperbolic sine, well, we just go ahead and switch the input and the output, so a point here is going to be 0, 0. Now in this case, it doesn't seem like there's much of a change here because, well, we were located at the origins, so it seems like, okay, not much is going on, but let me go ahead and compare it now to the cosh inverse of x evaluated at 1. So this one here, I'm just going to move it further down. There we go. And if we have here y equals to the cosh inverse of x, where we had a point, well, when the input was 1, our output was 0. In the case for its inverse, the hyperbolic cosine, cosh of x, then a point on this graph is going to be 0, 1. Or again, since we're dealing with an inverse function, we're just going to go ahead and switch the input and the output. And there we go. Now lastly, I want to go over the derivatives and integrals for the hyperbolic functions. As I mentioned before, we're not going to be going into detail for the derivation, but I wanted you guys to see them here. And use the formulas in case you need to find the derivatives. Now again, notice here that there are some similarities, but some differences. Now again, guys, I don't expect you to memorize these formulas. I do want you guys to know how to use them though. Now below are the integrals for some of the inverse hyperbolic functions. Now these integrals here, we would actually be able to get a derivation with the topics that we will be learning in chapter 8. But in the meantime though, here are the formulas, and if you were to encounter integrals that have this form, then you know which formulas to use. Now with that said, I want to go over one more example involving the inverse hyperbolic functions. So let's take a look at this one here. Problem 9, where we're being asked to find the equation for the line tangent to f of x equals to the tangent inverse, the tangent inverse of 2x when x is equal to 0. Alright, so if we're asked to find a tangent line, we know that we need a point and a slope. Now for the point here, well, we know that we're interested in the location when x is 0, but okay, if x is 0, what is the y value? Well, I'll put here when the input is 0, what is the output? What would be f of 0? So in this case, we're going to have here 0, comma. Now what will be f of 0? Well, this one here is going to be the tangent inverse of 0. Now what is the tangent inverse of 0? Well, using the formulas above here, we know that the tangent inverse then is going to be 1/2 times the ln of 1 plus 0 all over 1 minus 0, which is just going to give us 1/2 times the ln of 1, which is just 0. Okay, so we get the point here now. It's 0, 0. Now what about the slope? Well, the slope here is going to be the derivative evaluated at 0. So let's see, what would be our derivative evaluated at 0? Well, if our function is the tangent inverse of 2x, then the derivative will be, well, let's see. Again, using the formulas above, we're going to have here the following. Well, you know what? I will write the formula. The derivative of the tangent inverse of u is equals to u prime all over 1 minus u squared. So we're going to have here then our u is 2x. So u prime is going to be 2 divided by 1 minus u squared. So 1 minus 4x squared. Now if we go ahead and evaluate our derivative at 0, then we're going to get here 2 over 1 minus 0, which is just 2. So our slope then is equals to 2. So now that we have our point and our slope, using the point-slope form equation for our line, we're going to get y minus y1, which is 0, is equals to the slope, which we know it's 2, times x minus x1, which we know it's 0. So we're going to be obtaining the line y is equals to 2 times x. And there we go. Now we found the equation for the line tangent to the tangent inverse of 2x when x is 0. And this is where we will be stopping for this video. I'll see you guys later.